We are Dongfang and Jiahui. Today, we will present the paper titled A Probabilistic U-Net for Segmentation of Ambiguous Images. This paper is an extension of the original U-Net paper, which has a huge number of citations. U-Net was designed for medical image processing. As you can see that, by the time of our presentation, the original paper was cited for more than 13,000 times. We can see the importance of the U-Net for medical image research. While the paper that we presented today is published Advances in Neural Information Processing Systems, one of the most prestigious AI conference. So let's dive into this paper and see what's news for the extended version of U-Net. Before we articulate the objective, we want to learn the terminology, segmentation. What is segmentation? The figure is a demonstration of different information related to segmentation. A is raw image. B is overlay with ground truth segmentation. Different colors indicate different instances of the HeLa cells. C is the generated segmentation mask, white, foreground, black, background. Finally, D is the map with a pixel-wise loss weight to force the network to learn the border pixels. Many real-world vision problems suffer from inherent ambiguities. In clinical applications, for example, it might not be clear from a CT scan alone which particular region is cancer tissue. Therefore, a group of graders typically produces a set of diverse but plausible segmentations. The work considers the task of learning a distribution over segmentations given an input. They proposed a generative segmentation model based on a combination of a U-Net with a conditional variational autoencoder that is capable of efficiently producing an unlimited number of plausible hypotheses. The primary objective is to provide valuable predictions of segmentations for real-world applications, such as being used as clinical decision-making algorithms accounting for multiple plausible semantic segmentation hypotheses to provide possible diagnoses and recommend further actions to resolve the present ambiguities. The semantic segmentation task assigns a class label to each pixel in an image. While in many cases the context in the image provides sufficient information to resolve the ambiguities in this mapping, there exists an important class of images where even the full image context is not sufficient to resolve all ambiguities. Such ambiguities are common in medical imaging applications, e.g., in lung abnormalities segmentation from CT images. A lesion might be clearly visible, but the information about whether it is cancer tissue or not might not be available from this image alone. Similar ambiguities are also present in photos. E.g., a part of fur visible under the sofa might belong to a cat or a dog, but it is not possible from the image alone to resolve this ambiguity. Most existing segmentation algorithms either provide only one likely consistent hypothesis, e.g., all pixels belong to a cat, or a pixel-wise probability, e.g., each pixel is 50% cat and 50% dog. Especially in medical applications where a subsequent diagnosis or a treatment depends on the segmentation map, an algorithm that only provides the most likely hypothesis might lead to misdiagnosis and suboptimal treatment. Providing only pixel-wise probabilities ignores all covariances between the pixels, which makes a subsequent analysis much more difficult if not impossible. If multiple consistent hypotheses are provided, these can be directly propagated into the next step in a diagnosis pipeline. They can be used to suggest further diagnostic tests to resolve the ambiguities, or an expert with access to additional information can select the appropriate ones for the subsequent steps. The figure demonstrates the use of probabilistic-based segmentation. As we can see that, instead of using one color to predict one pixel point on the image, probabilistic-based method also provide the possibility distribution of the segmentation using the color of heat map. A body of work with different approaches towards probabilistic segmentation exists. The most common approaches provide independent pixel-wise probabilities. These models induce a probability distribution by using dropout over spatial features. Whereas this strategy fulfills this line of work's objective of quantifying the pixel-wise uncertainty, it produces inconsistent outputs. A simple way to produce plausible hypotheses is to learn an ensemble of deep models. While the outputs produced by ensembles are consistent, these methods are not necessarily diverse and ensembles are typically not able to learn the rare variance as their members are trained independently. In order to overcome this, several other approaches train models jointly using the oracle set loss, i.e. a loss that only accounts for the closest prediction to the ground truth. While many of the previous approaches are guaranteed to find the best diverse solutions, these are confined to structured problems whose dependencies can be described by tractable graphical models. The main contributions of this work are: 1. The proposed framework provides consistent segmentation maps instead of pixel-wise probabilities and can therefore give a joint likelihood of modes. 2. The proposed model can induce arbitrarily complex output distributions including the occurrence of very rare modes and is able to learn calibrated probabilities of segmentation modes. 3. Sampling from the proposed model is computationally cheap. 4. In contrast to many existing applications of deep generative models that can only be qualitatively evaluated, the proposed application and datasets allow quantitative performance evaluation including penalization of missing modes. The figure is the results of evaluations on two different datasets by using squared energy distance. It can be seen that the proposed method outperforms all its counterparts. The proposed work has heavier architecture compared to the original UNet. If we look at the figure A, the original UNet does not have prior net on the top section of the architecture. The concatenation of the prior net outputs and latent spaces will increase the computational costs. Also, because of the architecture of the proposed method, it requires more time to train and more complicated loss function. As shown in the figure B, the proposed method needs extra effort to train prior net in additional UNet. Although the computational load is affordable, the proposed method does require more complex training technique and heavier resource, and the inference time may be longer compared to the original one. This work has high impact for a number of reasons. First, of course, it provides a solution for medical image processing in terms of segment different tissues. It outperformed existing best approaches at that time. Since for medical image processing, it requires less time constraint but more demands for accuracy, the proposed method feeds the need of medical image processing requirement. In the second fold, it offers implications for general segmentation algorithm and how work can be done to improve the existing research. In this case, the proposed work changes the original UNet architecture by adding a prior net. More information were added in the latent layers for probability prediction for each pixel point and cluster of each part in the images. Finally, the proposed work has good generalization for segmentation work. Aside from being used for medical purposes, the proposed work can be used for other tasks. For instance, in the evaluation, the authors also used cityscapes, an autonomous driving dataset. Results indicate that the proposed work can be used for autonomous driving task too. There are a number of takeaways for us. First, we think it is to identify seminal study. As new scholars, we need to increase our reading list and try to cover the latest land-breaking research. By reading these research, it will help us to understand what is the research bar and limitation and potential directions that we can look at when find an interesting topic. Using this paper as an example, this proposed work is not built from the ground. On the contrast, this research was to further explore the exiting research limit and improve the existing best approach to the new limit. Second is that to do research, we only need to think about a little step forward at a time. Many people has the conception to have a land-breaking product, a giant leap. However, in reality, we should think about a step forward instead of a giant leap. Namely, if we can improve the accuracy, or efficiency, or robust in a notable scale, we can say that our research is meaningful. One step forward is a primary goal for any research. Researchers can accumulate these steps into a giant leap and better the science academy. Finally, we believe that any good research needs to provide values to the real application. As the proposed research, it can be used for medical image processing, but at the same time, it has a pretty good generalization, so that it can also be used for autonomous driving vehicles. For our future research, we believe that any inception of an idea towards a research need to have a solid ground for real applications too. Those 3 points are our takeaways for this paper. And thanks for listening.